So, welcome to the 20th lecture in mathematical finance. As you might recall, we currently face the task that we want to understand how we can optimally invest in a financial market, which were expressed optimally in the sense that we wanted to maximize the expected utility of our terminal investment. And this is, as you have seen or won't surprise you, is an optimization problem and has natural links to the optimization problems you might see or have seen in other courses about optimization. So I want to do a very brief detour to remind you or to prove for you some results in convex optimization. So what is the setting? The setting is that we have function f, which maps from Rn to R. And unsurprisingly, we want to talk about convex optimization. So we assume that f is a convex function, and we also want to assume that it is continuously differentiable. I mean, this is in general not needed, but well, we want to not push in the direction of optimization problems, so we make our life simpler and assume that we have a continuously differentiable function. And this is what if you keep in mind, this is it's always fulfilled if we have another utility differential utility function, right? So we assume that our utility function also possesses some regularity. And then we have also a set of constraints, which is here given by a set of function h j, right, mapping also from Rn to n, and well, so this might be more than one, are linear functions. So these are the linear constraints, which won't surprise you, will reflect the idea that we have a fixed terminal wealth, fixed initial wealth, sorry. Right, so the given the wealth at the beginning at time 0 are given. So we have we'll also face some constraints given by a linear function. Just a side remark, which you hopefully have seen at some point in one of your analysis courses, is okay, if I have a convex function, and here in the setting f it's a continuously differentiable function, then it's convex if and only if I can estimate the function at point x by the function evaluated at point y plus difference of x and y, and the scalar product and the derivative of f at time x. Right? So if you're wondering, so here I changed I mean, I'm not making this prime because we have here a as a function which acts on Rm, so this is a vector. Okay. So far so good, and now we want to. Oh, what did I do? Okay, and now let us formulate the optimization problem we want to briefly study. So what is the problem? Consider the convex optimization problem So for later reference, let it call COP, so convex optimization problem. And now we want to minimize well, x and n, the function that f of x, right? So we want to find a global minimum of this convex function f under the constraint that the linear constraints are fulfilled, in the sense that if I evaluated my function hj at point x, it has to be 0, right? So this is a linear function, so we talk about linear constraints here. And we might have q of them right here. That's great. So this is the problem we are facing. And well, how can we solve this problem? And you might have seen it also in some economy courses. It's a nonlinear optimization problem, right? But it's has linear constraints here. So the way to find minimizer to this problem is, one classical approach is to write down the corresponding Lagrange function. So this is the Lagrange method, which identifies or characterizes you the minimizer x star to this problem. So find a minimizer star to our COP problem, so convex optimization problem. Introduce the Lagrange function. Usually denoted by L, which has as the pre-image also the Rn, right? This is the pre-image of F, and then I have all the constraints. So I have here an extra parameter, which is my Lagrange multiplier, which is also an input of my Lagrange function, mapping to R. And now, what is it? Well, so my function L applied to x and y is defined as, well, I just take my function I want to maximize, or minimize here, sorry, minimize my function f, which is my target function I want to minimize. And now I penalize it with the linear constraints. And so these are my linear constraints, and then I weight them by the lambda, right? This is a vector in RQ, as I have Q linear constraints. Okay. Okay. This is function, and well, now in order to solve this convex optimization problem, well, I just need to take the derivative of these functions here, of the Lagrange function, and keep in mind the linear constraints. Right, so what is how can we have characterized the optimizer, minimizer x star here? Well, we write down basically the derivatives plus the linear constraint, and this is because you can do it in a much more complex setting as well, called the Karush-Kuhn-Tucker condition. Which allows to then characterize the minimizer later on. So this Karush, Kuhn, Tucker. And as this is rather long, so K, K, T condition. Well, very simple. I mean, it's the function which is differentiable, so you know how to find a global maximum. So we want to take the derivative of the Lagrange function. So this is just spelled out for you. So you take the derivative of f and then plus you want to also keep the linear constraint in mind. So you take also the derivative here as of the Lagrange function, which means you have also to differentiate the linear constraints here, which is okay. This is easy because these are linear functions, so that's not an issue. And then, of course, you want to keep in mind that the linear constraints are fulfilled. Okay, and this is Q linear constraints, so you have to do it for all of them. Okay, and you won't be surprised if you have a point x star and the corresponding Lagrange multiplier lambda star fulfilling this condition. It will be a maximizer or minimizer. Okay. So x star and with Lagrange multiplier Gator lambda star is called Karush-Kuhn-Tucker point if the KKT conditions are fulfilled at this point. All right. So I guess you have probably seen similar things already. So now let me formulate and then of course prove for you for completeness reasons that this is actually what we need to find in order to solve a convex minimization problem. Okay. So that's the next proposition. And so don't worry, and this is all what I want to do in this direction, and then we come back to our financially motivated problem of portfolio optimization. All right, so this is position 5 and 6.9, which tells you, well, if I have such an X star, and it is a KKT point, so Karush-Kuhn-Tucker point. Well, of course, of our convex optimization problem, right? So it has to be like in the context of this setting here. Then this point X star is the global minimum. Oh, actually it's minimum. of our convex optimization problem. Right? And the proof turns out to be not really hard. But as I said, for completeness reason, I want to at least briefly go through it. So let's do it. And then we want, of course, I mean, then why do we want to do this now is because then in a minute, okay, a couple of minutes, we want to apply it to our original problem. Okay, so let's take this KKT point. And this means also here that there's a multiplier with a multiplier lambda star, right? So this is part of the definition that I find this X star, that I also could find the corresponding Lagrange multiplier lambda star. Okay. Well, what does it imply? So if I plug in my KKT point with this multiplier lambda star, right? The linear. So this means, thanks to the linear constraint here, the Lagrange, we go up here, the Lagrange function as defined here is just the function f itself. Okay, that's nice. So yeah, this is f, right? The Lagrange function applied to this KKT point is just the function f itself. And so this is our first observation. The second observation is, well, if I take point x, which is an arbitrary one, and I assume that it fulfills our linear constraint condition. So linear constraint here, let me call this here, as in the lecture notes, 6.1. Right. So this is just a linear constraint of our optimization problem. Well, if I have a point, oh, this is only, which fulfills our linear constraint, well, then I know that f is actually bigger or equal than Lagrange function by 2. Okay. Because if the linear constraint are fulfilled, this corrector term here is just gone. So the penalization is gone because the linear constraint is fulfilled. So this is just the function f. Okay. And now, at some point, of course, you won't be surprised, we want to use the convexity, and I think this is now the right moment to use it. So if we fix these lambdas, and this is the fixed one, for the function x mapping to the Lagrange function x lambda star. So if I fix the lambda star, which is here done because, well, we started with the lambda star, which we have chosen. Well, this is a convex function, right? Because, right, if you look at the definition, this is just a convex function plus a linear function, which is again a convex function. Okay, and now we recall what we have learned about convex functions. So we have these nice estimate, which is actually equivalent characterization convex functions if they are continuously differentiable, which is the case. Okay, so if I want to estimate the difference between f evaluated x minus x evaluated f of my x star, which hopefully is positive, because then we have a global minimum if it's positive for all other x. This is now, well, we have here the estimate. So we use our two estimates we have seen. So we just plug in here now these two observations. So we can express this as Lagrange function evaluated at lambda star minus the Lagrange function evaluated x star lambda star. Well, but this is now a convex function, as we just have observed. So I can estimate it the difference of x and x star. Then I have to take the scalar product with respect to the derivative of the Lagrange function at the point lambda x star lambda star, and the derivative is taken with respect to the x component here. But this is a KKT point in particular. This means the derivative of the Lagrange function has to be 0. So what do we see here? That's 0. Since yeah. Good. And okay. Now we are done, right? Because we can reformulate this equation by saying f evaluated at any point x, which has to fulfill our linear constraint, is bigger or equal than f fulfilled at our point x star for all x in xn, which fulfills our linear constraint condition. So this was 6.1. Oh. Okay, so this completes our proof. All right, that's great. Okay. Okay, now we understood how to solve a convex optimization, a minimization problem. So let us come back to what we actually wanted to do. So back to folio. Optimization in complete markets. So the aim is, our approach is the martingale method. Right? So what we understood, if we want to solve in a complete market, this portfolio optimization, which ask us to maximize the expected utility of our terminal wealth, we understood we might want to split the problem into two problems. And one is an optimization problem saying, okay, I just want to optimize overall payoffs, which are just random variables. And then I want to represent these payoffs by a trading strategy, so by a replicating trading strategy. So this was our representation problem, and this was easy to solve for us because we know it's a complete market, so we can replicate any payoff by trading into the market. So this is all right. So so what is this second? Let me recall the setting. So our setting is we have market, right, which is finite, arbitrage free, and complete. Right? And now we wanted to solve the auxiliary optimization problem. Which were so given you have an initial capital x0, so this is the amount of money we have, and we wanted to start with something positive because otherwise it's so we want to solve this was our auxiliary problem, so let's call it P tilde, which we're saying, okay, let's maximize the expected utility over all random variables x in this set calligraphic x, script x, where u is in order. So it has to be like, it has to be at least one time continuously differentiable, and you have this behavior to infinity and to zero. This is our utility function we want to pick, or the class of utility function we want to pick. Which is mainly because we want, I mean, this is economically justified and allows us to develop the math rigorously. And then we had here set x, right, where x is ft, so just a random variable, such that the price we have to pay is x0. Right? So these are all the payoffs which have the price x0. Well, you can express it. So, okay, just a side remark as we need it. There exists a unique equivalent martingale measure Q, since the market here is complete and finite and arbitrage free. So these are the first and second fundamental theorem in asset pricing. All right. So if you have first and second fundamental theorem of asset pricing, right? If you feel like, you're not sure, that's a good moment to go back and check that this is right. Okay. So wait, now we need to reflect for a moment the problem we have here. So what we see here, if you look at P star, that this is concave. Maximization problem. with linear constraints. Okay. And well, 10 minutes ago, I was showing you how to solve a convex minimization problem with linear constraints. Okay, now you can say I'm a bit confused, but hopefully I did the right thing. And yes, I did, because, well, what we note here, if you look at this maximization problem, right? So, right, if we want to maximize the expected utility of X, well, this is the same as saying, well, I minimize overall X in X, and then I minimize the function minus U, then apply this minus U function to X, right? And now minus a convex function, minus a convex function is a concave function. Convex minus a concave function. The utility function will always assume to be concave. I would take minus, so I get a convex function. Right? So this is also a side remark. Okay. So indeed, we can use, hopefully, the theory I just developed. And now, well, this second observation is, and this is a one we have used already several times, is, well, since we have already here on a finite market, so maybe should make this, sorry for this. Right, so this is our first observation. And the second one is, well, since we have a finite market, so we have here a finite underlying probability space, we can again use our nice trick to identify random variables with vector in Rm. And this brings us exactly into the setting that we can use real analysis or here real convex analysis or optimization to solve our portfolio optimization problem. So we can identify random variables with vectors in Rm, so with values in Rm. Okay, so these are the two observations we want to use in order to apply the theory about convex minimization to this auxiliary problem, which is actually a probabilistic problem because we want to maximize here over random variables. But if you do it without this assumption of finite probability space, you need to be careful because you need to have compactness results in the set of random variables. And for this, I would invite you to keep studying probability theory. Of course, this is possible, but unfortunately, not yet for us. All right, so let's try this and solve this problem. Or solve it. Or let's try and see if it works. First thing I want to do is, I want to use in the second step to make everything to a real analysis problem. And at the first step, I want to reformulate here the linear constraint. So if you right, look here, we have here measure Q, and here we do the optimization problem under the physical measure P. So I want to reformulate with everything with respect to the measure P. We know how to do it. We just need to consider the radon-nicotium density in order to express this linear constraint with respect to P. So right. Yeah. Let's solve the P star. Okay. Use the radon-nicotium density P to Q. Multiplied with the factor, right? So I just want to get rid of the discounting factor, so I multiplied with 1 over P, with 1 over B. Which this is here the discounting factor you have here and there as well. Since here I don't care so much about discounting, so let me put it into the radon-nicotium density, and then it's called state price density. Anyway, so what is this? This is just the random variable Z defined as 1 over BT. And since we have here a finite probability space, well, we just can write down the radon-nicotium density, which is just the probability of an element omega I. Oh, okay, this can be any omega. So let's write it again. Omega, which is just an element in our probability space omega, divided by the probability under P. Okay, so here this abstract radon-nicotium density modular factor is just simple random variable. Okay, and the nice thing is, well, hence, if I have an X in our X filter, well, sorry, this was, we see that if I want to calculate the expectation under Q of X divided to BT, and I want to do this because this is our linear constraint, this is nothing else than the expected value under P of X multiplied with Z. Right? So this is, I mean, the radon-nicotium density. Okay. So this was the first thing. And now I want to use the second observation, which I stated here under 2 already. Okay, I want to identify random variables with vectors. Right. Let's break here. So so what do I have? We have here an X and a Z. These are the random variables X and Z with vectors, which we call again X and Z. So, because I mean, this is a one-to-one correspondency here, right? So since our probability has m elements, we have m different entries, and this entry xi is given by the random variable evaluated at omega I, and omega I is an element in omega, right? So this is one of our elements in the probability space, and the same can be done for z. So this is just z evaluated at omega I. Okay, so this is a trick you have seen several times, so I hope this is not scary anymore. Okay, and now let's solve the problem. So let's deal with p tilde. Well, we know what to do, right? We want to consider the associated Lagrange function. L of x, right? X is now a vector in Rm. Right? So this is, let's go up to our problem lambda p, right? So we have your function. So this is the function with the expected value of u applied to x. And if you understand x as a vector in Rm, well, this is just a sum. So it's just a, it's a sum over the values of u applied. So the value you get if you apply u to xi multiplied with the probability that it appears. So this is indeed a real function. Multiplier. And we need this Lagrange multiplier to express the linear constraint or to get it into our problem. And here the linear constraint is just a, so this is 1, so we have here just lambda and r. So Lagrange function associated to our optimization problem here is nothing else. So that's the definition. So this is my convex function. Okay, I'm a bit lazy here, so let me drop the minus. Then we have here the penalization. That's right. So this is the linear constraint from the linear constraint given by the sect x script x. And this is my convex function, right? So you see, I just swapped to the sign because, I mean, I could also make here minus here plus, but this doesn't matter. We want to consider the moment when it's 0. All right. Now that you all can see that this is indeed a function from Rm. Let me calculate for you the expectation here. That you see, well, this is good. Well, this is just a concave function or convex function, depending how you see it. And then you calculate here also the second expected value. Again, you have to weight it with the probability that an omega I appears. Then you have here zi xi, right? These are the values of the random variables. And then you have minus the. And so, right, so just to come back a bit to the. So what do you have here? And I will delete it in a second. Right, so this is our linear constraint, and we want to, so we pull the x0 on the other side to have that our linear constraint is a linear function with the, precisely enough, a fine function, so which has to be 0, right? This is to bring it in the form we have seen on our detour about convex optimization. Okay, so that's nice. And well, let me rearrange it so that's not looks so long. So I have the probability that omega I appears, and then I have just the utility function evaluated at xi minus lambda zi xi minus, and now I have minus minus, so that's a plus lambda xi. Okay. So that's my Lagrange function associated to my optimization problem. Okay. And now I know what to do. So we are looking for KKT point X star with multiplier. A multiplicator lambda star. So what do we have here? With two conditions. I mean, this is the two conditions. So first, we want to take the derivative of the Lagrange function with respect to x, and this has to be if I plug Karush Kuhn Tucker point in it, it has to be 0, right? What does it mean? So this means I want that 0 is equal to, so each component has to be 0. All right, so I have to take the derivative with respect to the partial derivative with respect to xi of lambda I, right? And then what? Okay, let me show you the function again so that you can follow my calculation. Okay, so all the summons disappear except the eth one, and then I have here for the eth one, I have the factor, the probability that omega I appears, multiply with, well, okay, here I have to, u depends on xi, so I have to take the derivative of u. I have my point x star I, and now, well, the initial value disappears, but I still have minus lambda zi xi. Okay, that's another bracket. Wait, and I can do this, or should do this, for all I from 1 up to m. Okay. So this is the first condition. I want that the derivative of the Lagrange function is 0. And the second one is I want that my linear constraints are fulfilled. So lambda star 0. And you know, okay, this has to be 0, and you know what it is, right? This is so 2, right? Okay, so these are the same. All right, so this is the linear constraint you have here, or you have here, right? So these are the two linear constraint. Feel free to use the formulation you prefer. All right. Okay. Okay, so how can we find now this X star and lambda star? Well, we have these two conditions which have to be fulfilled. So let me also reform them so that we see what the value has to be. So we start with the first one. So if you use 1, so I, and since we have included in our assumption of a finite probability space, the probability should be strictly positive for each element in omega. So we look at this condition. So this is always positive. So the second term here has to be turned. I mean, this is okay. Right. So this multiplied with this has to be equal to this. This term has to be 0. So the derivative of u evaluated at x star I has to be equal to lambda star. Oh, I forgot to start here. Xi, and this has, of course, to hold for all. Okay, so that's an equation. The first equation, my x star and lambda star have to fulfill, and now I want to get hands on this x star. So we observe that I have an inverse function of the strictly increasing and continuous function u prime. Right, so by our assumption here, the derivative of our utility function is strictly increasing. Yes, decreasing. Oh, sorry. We have a concave function, so it has to be decreasing. And by assumption, by our regularity assumption, where it was continuously differentiable, so the derivative is also continuously, right? There was another differential equation, differential utility function. So this was just assumed. So let us define now I to be the inverse of this function u prime. So what you also know, that this is unequal to 0. So we need to have the lambda. So we need to, the lambda has to be strictly positive, and we can Right, we apply the inverse function to this equation here. So this is the equation. So I get rid of the u prime, so I get here the x star I, and I can do it for each component. So forget this component. Okay. So and this is for I up to m. Okay. 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 So this is the equation I get from using the first condition here. So the condition I. And now I want to use the second one as well. So due to IR, we need, right? So the moment we find lambda star, we have by this condition x star I, right? So if we have a lambda star, we are done. So we need to find lambda star. So that the second condition is fulfilled. So we need to choose lambda star such that here our linear constraint is fulfilled. Right, we know what x star is, so we can plug in here I. So what we just have learned, star z divided by bt. And then now let's go back to our process z. So let's swap to the measure p. Right, and this has to be x0. Okay. So now the question is, why does this lambda star exist? Well, since we have here continuous function lambda mapping to I of lambda z, continuous and decreasing, y the intermediate value theorem that exists lambda star, since and fulfilling here the equation we want to have, since, or if you look at the limit lambda going to 0, this goes to plus infinity, and if you look at the limit lambda going to, lambda going to 0 gives you, by the initial conditioned, this goes up to infinity, and going to lambda to infinity gives you that this goes up to minus infinity. Okay. And since where x star is something between 0 and infinity, you know, and this is a continuous function, like going from minus infinity, from minus infinity to plus infinity, it has to cross at some point x0. Okay, so basically we can now put our findings into a proposition which tells us we can really solve this, the original. Right, so basically what we have seen now, we can solve the auxiliary problem. So there exists just a lambda star and an x star which fulfills our KKT conditions. So there is a solution x star to this auxiliary optimization problem here, p tilde, and this can we now use to solve the original optimization we wanted to solve. Okay, so let's come back to this, and let me directly give you the theorem, and then we just need to apply what we have learned in order to prove it. So this is theorem 6.10. Okay. There exists self-financing trading strategy lambda star phi star solving the portfolio optimization problem. Okay, what does it mean? So just, I mean, this is now what the statement is. So this means if I consider the expected utility of the terminal valve generated by these, we're trading the market with respect to phi prime, this is equal to the maximum over all self-financing trading strategy, which start with the same initial capital, and then I consider the maximum of all expected utility of the terminal valve with respect to these trading strategies. Right, and phi prime has to fulfill our linear constraint, so it has to be x0 at the beginning. And here, the supremum, as I said, or the maximum, because the supremum was attended, so it's a maximum. Taken over all self-financing trading strategies. Fine. Such that the initial capital I need to implement this trading strategy is exactly x0. Yeah. Okay, so this is the original portfolio optimization problem we started with at the beginning of last lecture. And now I promised you that I can take all the results we derived, and the proof is not too hard anymore because we did already all the mathematics. So we take our X star. Is a solution to, right? So this X star is exactly what I derived here. And this is the solution by taking our proposition over the convex, so the existence of a global minimum, to our convex minimization problem. So this is nice. And now I just need to recall you how I can find now. So since the market here is complete, and arbitrage free, of course, otherwise yeah. So there exists self-financing, right? So if I have a complete market, I can find a replicating strategy for all claims. Let's call it, as in the theorem, phi star, such that the terminal wealth I can generate by trading with respect to phi prime is exactly X star, and by construction and this is how we formulate our linear constraints. We have that the initial value we need to implement this one is X. Okay. Right. So as a conclusion here, this X star is a solution to P. Okay. All right. Here we are. So we were able to solve the portfolio optimization problem in a complete market with this arbitrage free as well, because otherwise it's a degenerated problem. And now, I mean, if we plug in more explicit utility function like the log or the power utility, we can actually really calculate these trading strategies, which you will, or at least be invited to do on the problem sheets to solve this more rigorously. I mean, no, not more rigorously, sorry, to solve this more explicitly. Because here, I mean, as long as we have a general inada utility function, well, that's how far it gets. Okay. Okay, this was the case of a complete market. Now we also, of course, want to understand, because this is more realistic, how can we solve this problem in an incomplete market? So in principle, this method can be extended a bit further to incomplete markets as well. But I want to develop a different approach, which of course also works in a complete market, but it's, I mean, the motivation is now because we want to consider incomplete market as well. All right. Optimization in incomplete markets. Okay. What do we do? Okay, the setting. I mean, it's usual, right? So we have here a market. It's, I mean, I'm not want to specify if it's arbitrage free or not. I mean, we will do this later on and understand. We can actually characterize, and this is what we do at the beginning of next lecture, to characterize the arbitrage freeness of the market with an if and only if condition that the utility maximization problem has a solution. So that was usually, we have now a general financial market. Lying market. And just to fix one thing to make my life or my notation simpler, as usual, the risk-free asset at the time 0 is normalized to 1. Okay. In this setting, I mean, I want to slightly modify the notation because it makes my life easier. And notation, it's not changed. I want to take the bookkeeping in a different way, because this is also the standard way to do it in these portfolio optimization theories. Right. So instead of keeping track of the number of shares I hold in each of the different assets, I want to keep track of the amount I have invested in this different class of, I mean, the D+1 assets. Because in the end, we care about the terminal wealth and not about the amount, I mean, the number of assets we hold. So if I have a self-financing trading strategy, right, so I have here consisting of a position in the risk-free asset and in my de-risky assets. And I mean, of course, I only want to consider self-financing trading strategies because this is our standing assumption. Right. And now I would like to introduce you, well, that's what I said, a new process. So we define psi. Okay, we have which this corresponds to the amount we have in the risk-key asset, and then we have the risk-free assets here, right? Okay, let me exclude this one. And well, as usual, yeah, right. This is, we have our amount in the risk-free asset and the different amounts in the risky assets. Right. And what we decide, as I said, so phi0, psi0, sorry, psi0 at t is defined of the amount I have invested in the risky asset, right? So I take my B t+1, which is what I have at the beginning of the t trading period. So this is here ft measurable. And then I multiply it with the amount, I mean, with the price of the risk-free asset. So this is the total amount I have invested in the risk-free asset, and I do the same for the risky asset. So CKT, the amount I have invested in the K asset at time t. So that's it. And this is of course definition for, right? I have D of these assets, so from K from 1 to D. And I have, of course, right, and I can extend this also for the capital T as well, but I mean, this is, I mean, then there's the terminal time, so it's not important anymore. So what is here, what you have? Note what I verbally explained is the amount invested in the K risky asset at time t. Okay, that's the ninth thing is here, because I only care about the terminal about the wealth, right? So if I look at the wealth at time t, or the value I am generated by trading with respect to phi at time t, well, this is now nothing else than the sum of these, the amounts I have invested in each of the D+1 assets. No, and this is, and this is here. Now okay. Let me call this V of psi at time t. So this. T 0 to t. All right. Okay, this makes my life. I mean, this is nice and expression. Now let me also fix some useful notation. So so I haven't specified how my risk-free asset looks like. So in principle, I mean, I introduced this little RT, which depends on the time. So this is my interest rate over the teeth period, teeth plus 1 period. And then I can do the same. Oh, what's this? Why isn't it? Okay. Sorry. All right, I look at the kth asset, and I introduce here my k tilde. This is just an auxiliary random variable. But what I actually want to have is here plus t minus rt, right? Where here this is my return from the kth asset, right? So this is, and well, what do we need further? Well, you won't be surprised. So the corresponding vectors of these R tilde and R, I mean, they are defined just as without the index. So if I drop the upper index here, I mean the vector consisting of all the random variables here, and the same for the return here. Reversing. Okay. A few minutes left. It's good. Okay, these are of course also definitions, right? Because we haven't used it. Okay. So let me finish here with the deriving. I mean, understanding a bit. I mean, what I gain from these different or slightly changed way of bookkeeping. So the goal I want to achieve here is now I want to express the value at time t in terms of these parameters, and then the value at time t minus 1, right? So I want to have the vt is a function of vt minus 1, and then depending on these parameters, right? These are random parameters. So okay, so I have here my self-financing trading strategy. What do I have from this? I mean, this is the definition of self-financing. I know that, well, what I hold at the end of the T trading period, the money I have at the end of the T trading period has to be the same as the money I have at the beginning of the T plus 1 trading period. So this is just a definition of self-financing. This means that I use this to express here the value process at time t. So what is this? This is okay, the amount of money I have invested in the risk-free asset plus, well, okay, the amount I have in the other one. So this is, the E is just a vector consisting of only ones in RD, right? So this is just right. What is this? So now I want to use the self-financing. So this is nothing else than the amount I have at time t minus 1, and then all the changes have to come from the changes in the interest rate here, and here the same, right? So the amount I have at time t minus 1 multiplied with the returns. Okay, that's good. Okay, what do we get from this? Well, if I look now at the difference of my the amount of money I have at time t and what I had at time t minus 1, right? So let us use directly I mean, here for t, let us use the formula I just have derived. So this here. Plus and now, well, okay, let us use the definition again. So this is for t minus 1. So I have here C0 t minus 1 minus, let's see, there at time t minus 1. And then here E, right? What is this? Sorry. Okay. And now, what can I do? I can pull also the C0 t minus 1 and this one are canceling. So I have C0 at time t minus 1 multiplied with RT. So that's so nice. Plus, and then I have these. So C at time t minus 1, scalar product with R tilde t minus the vector E. Okay. Okay. Okay, so what do I learn from this? So if I look at the value I have at time t, well, this is obviously equal to the amount I have at time t minus 1 and the difference. So this is a usual telescoping argument. No. Right. T minus 1. Okay. Well, and now I just calculated here the difference, right? So I want to use this. So let me plug it in. So that's C, G. Okay. Right, okay. So this is, well, as I said, I mean, just plugging in what I learned from the calculation before. Right. Oh, this is, of course, this has to be same, right? Here I didn't want it to change anything. Right, this is okay. So this is what I keep, and now I express this term. So the value I have in the risk-free asset in terms of the overall money I have at time t minus 1. And then I have to subtract all the amount I hold in the risky asset, the de-risky assets. Okay, I shouldn't forget this random interest rate. Plus, okay, yeah, I didn't do anything. Okay. Okay, let's can simplify this expression here now. This is the value I have at time t minus 1 multiplied with 1 plus RT. So these are the first two summands. And how can I simplify the other part? Okay, I have here C at time t minus 1. Now I put all these things here together. So I have R tilde t minus E. So this comes from here. And then I have here a factor R. So I have E minus RT. E minus E multiplied with RT. Right? Okay. And now I pull out my discounting factor, or the growth in the interest rate. So I have here this factor, and if I pull this out, okay, I have here just the value. So this is coming from here. Plus, what do I have here as well? So I have psi at time t minus 1, scalar product with, okay, R tilde t, I have to divide it by RT, 1 plus RT minus E. Okay, and now this can simplify it again a bit. Right. This is okay, just my R, so T minus, oh, that's it. Sorry. T. Right. So long story, I mean, slightly long calculation. So this is gives me here, let me label it. I will use this later. So this gives me a recursion formula that I can express the value, the amount of money I have at time t in terms of what I have at time t minus 1, and then just the growth I have in the market, right? Depending how I choose my positions, of course. All right. And next time, then we will come back to, really solve the portfolio optimization problem in an incomplete market as well. All right. Thank you very much.